This is a Total production. Hello everyone. This will act as our last practice video focusing specifically on proton NMR. So what I've got here, there's actually 6 proton NMR spectra, but they're in reference to, hey, here's a handful of molecules, tell me which spectra coincides to which molecule. So when we go and do this in proton NMR, you got to remember this is HNMR. So this is signals that we get based off the hydrogens in the structure. So without getting too fancy in the explanations, one of the things you want to pay attention to is, well, first, whether you're talking about proton NMR or carbon-13, if you need to move on to carbon-13. But regardless, you want to look at the molecule and see, is there any symmetry whatsoever in our molecules? All right, and that will kind of give you an idea of how many signals you should see. All right, so for instance, when we look at this first one here, I can't see anywhere where there's symmetry about the molecule. So that means that there should be 1, 2, 3, 4, 5 different signals because there's 5 different sets of protons or hydrogens. All right, next I look at this guy. I don't see symmetry anywhere in the structure. So in terms of where the hydrogens are, I should have I should have 1, 2, 3, 4 different signals. So that in and of itself, 5 versus 4, would make these two very easy to differentiate if we had example spectra of both, which we do. Next up, we've got this molecule, and it does have a plane of symmetry right here. So it actually, these hydrogens and these hydrogens would give me the same signal. So it's going to count as 1. While these hydrogens and these hydrogens would give me the same signal. So I only have 2 signals here. So just looking at that, 5, 4, and 2, I can look at this. So just looking at this of 5 signals, 4 signals, 2 signals, I can look at each of these 3 and say, hey, that's got 1, 2, 3, 4 signals. So this right here has to be this structure. So this corresponds to that because it has 4 signals. All right, I look down at this guy right here, and it's got 1, 2, 3, 4, 5 signals. So that's got to be this aldehyde here. And then 1, 2, 3, 4, 5, yeah. And so then I look at this guy, it only has 2 signals, 1 and 2. So that tells me, hey, that's got to be this ketone right here. All right, now with that in mind, right, that was very easy. And sometimes it can be that easy. But just in case it's not that easy for you in the future, I wanted to go ahead and break down like what each one of these signals, why they look the way they do, right? So I don't just now want to identify the molecule. I want to look at, say, these 3 hydrogens here, right? Those 3 hydrogens there. If I look at them, that gives me, and I'm going to label this on the same thing up here. These are my A hydrogens. When I look at those, which of these 4 signals corresponds to that? Well, in order to figure that out, I need to look at how many neighbors those hydrogens have. So think of the carbons as houses, and think of the hydrogens in them as the actual people that live in the houses, right? The neighbors. So when you go, this house only has 1 neighboring house, this guy right here, and it has no hydrogens in it. So this has 0 neighbors. So you have to use the n+1 rule, which would be 0 plus 1 or 1. So these 3 hydrogens would give me a signal that's only 1 peak, right? And so I'm looking at these. You see how you got this signal has 1, 2, 3 peaks in it. This signal has 1. Guess what? I bet that's my A hydrogens. This has 6, and you can't really see all of them, but it's 1, 2, 3, 4, 5, 6. And this one has 3, 1, 2, 3. So only one of my hydrogen signals is a singlet, so odds are these hydrogens are what gave me that specific signal. Now I do the same thing to these two hydrogens. Right up here I labeled those as B. And how many neighbors do they have? Well, they only have a neighbor here that has two hydrogens. So they have an N plus 1 or a 2 plus 1 to give me a triplet, to give me 3. But I have two triplets. So let's keep going for a second. All right. Next up we have these two. Now these two, which I would label as C, they have hydrogen neighbors on this side, and they have 3 hydrogen neighbors on this side. So they have a total of 5 neighbors. So I'd have to look at 5 plus 1 or 6. So that sextet right here, right, 6, comes from hydrogens that I labeled as C. Okay. Next up, these 3, right, these would all be D. I'm going to consider these equivalent, right, because they're all equivalent because they live in the same house. Okay. So these D hydrogens, their only neighbors are these two. So their N plus 1 is actually 2 plus 1 or 3. So here's my two triplets, B and D. So how do I figure out which ones are which? Well, you notice this triplet is at a higher ppm, which we call downfield, compared to this triplet. So how do we get that? Well, as hydrogens get closer to electron withdrawing groups, or closer to electronegative atoms, or closer to pi bonds, they tend to become more de-shielded. And so these B hydrogens are closest to this electronegative or electron withdrawing group. So I would expect these hydrogens to give me a triplet that's at higher number. So I would suspect that the B hydrogens gave me this triplet, and that the D hydrogens gave me that triplet. All right, next up, when I look at these, all right, I'm going to label them the same way. I've got A, I got 2 hydrogens here to give me B, 2 hydrogens here to give me C, 2 hydrogens here to give me D, and CH3, that'll give me the E's. All right, so of my 5 signals, this is kind of one of the most unique signals that you can get, an aldehyde hydrogen. Right, that hydrogen is bound directly to the carbon with the double bond. And these hydrogen signals usually pop up somewhere around 10. So that triplet right there makes sense as signal A, just based off of how downfield it is. But the other thing to notice is that it's a triplet. And so when you look, right, the hydrogen lives in this house, right? So its neighboring house only has 2. So this does have the N plus 1 or the 2 plus 1 to give you 3. So it makes sense for A to be a triplet. All right, we look at our B signal, and what do we got? We've got 1, 2, 3. Yeah, so 3. But we don't have a quartet anymore. So, yeah, we don't have a quartet. So the big deal with these B hydrogens here is that technically, because this aldehyde hydrogen is most likely invisible to them, so this is probably going to give us a triplet right here, the B hydrogens. So it really only sees these 2. Right, so that'll be 2 plus 1 to give us 3. All right, now we have 2 triplets, but odds are, right, there's a triplet that's more downfield than the other triplet. So I'm banking all my money on that this triplet that is the most downfield are the hydrogens that are closest to this carbonyl, to this double bonded oxygen. So I'm going to go ahead and label these as B, because we already saw that in the previous example. Now these 2 hydrogens, they have 2 neighbors on this side, 2 neighbors on that. So they have 4 neighbors plus 1, that would give me 5. That's also called a quintet, and we only have 1 quintet. So this would be due to my C hydrogens, my quintet here. I'm betting my D is the sextet, because when I look at the D hydrogens, they have 2 neighbors here, 3 neighbors there. So that's a total of 5. So 5 plus 1 or 6. So 6 would be a sextet right here. So that has got to be D. And our remaining triplet is probably our E, but let's check it real quick. These 3 hydrogens only have 2 neighbors. 2 plus 1 equals 3, so E gives me a triplet, so that would be my E hydrogens. All right, and then lastly, I'm only going to do one side of this because we talked about how this had symmetry. So these two hydrogens, right, they only have, well, let me write CH3 here. These two hydrogens only have 3 neighbors, so it'd be 3 plus 1 or 4, which is a quartet. And that makes sense because those hydrogens are closest to the carbonyl. So what did I label those? I labeled those as A. So the A hydrogens would be my quartet. That would mean my B hydrogens have to be my triplet. Does it match though? These 3 have 2 neighbors, so 2 plus 1 gives me that triplet. So yeah. Okay, so you can use both of these, right? Look at the symmetry, count up the number of signals, and that'll kind of help you determine the answer. But if you need to, you can break it apart and understand these triplets, singlets, quartets, quintets, all that good stuff. All right, and I've got one more practice problem here real quick. So when we look at this one, right, we've got 4 options now. And in looking at this, right, I kind of want to break apart, do I see symmetry components anywhere? The whole molecule doesn't have to be symmetric, and there's an example of that. So I'll say that again when I get to it. So when we look at this one does not have symmetry anywhere. So we expect it to actually have each set of hydrogens, A, B, C, D, they're going to give us their own unique signal. So I would expect 4 signals. And we have a 4, a 3, and a 1. But let's make sure, because we actually have an extra one, so we want to make sure which one is which. All right, next up we have this guy. There's no symmetry in this guy either, so that means we have 1, 2, 3, 4. So we have 4 signals for that. So we're actually going to have to look at this and figure out which one of these 2 it is. All right, for this one, this actually does have symmetry in one part of it. That means these 2 sets of hydrogens are identical. So I labeled them both as A. Then I've got a hydrogen here as B and a hydrogen there as C. So this would only have 3 signals. So I can go ahead and say probably that's this one right here because it only has 3 signals. Now this one has a whole bunch of symmetry, right? Pretty much because all 3 of these methyl groups are attached to the same carbon, we know that all of those are equivalent. And that accounts for all of the hydrogens in the molecule. So it should only have 1 signal, and that's what we have right down here at the bottom, which is a singlet, right? Which means do these 3, so like pick this CH3 right here. Does it have any neighboring hydrogens right there? No, there's no hydrogens there. So it would be 0 plus 1 or 1. So that would give me a singlet. So that makes perfect sense. So that is that. Okay. And then therefore the 3 signals is that one. Okay. Now, in order to determine, right, which of these 2 molecules this is, I need to kind of figure out, well, what are the signals I would get for these? Right, because I've got a triplet, a quintet, a sextet, and a triplet. So let's look. These 2 hydrogens, well, yeah, let's do it down here. Alright, so there I've kind of shown them all out. So here, these 2 hydrogens have only these 2 neighbors. So I would get 2 plus 1 or 3. So I should get a triplet for one of them, and there is a triplet in it. So now look at these 2. They have 1, 2, 3, 4 neighbors. So they would get 4 plus 1 or a 5. Do I have a quintet? I do have a quintet. Let's look at these 2. These 2 hydrogens have 3 on this side, 2 on that side. So it'll be 5 plus 1 or a sextet. And then these 3 only have those 2 as neighbors. So they would be a 2 plus 1 or a triplet. So do I see 2 triplets, a quintet, and a sextet? 1, 2 triplets, a quintet, and a sextet. Alright, but let's not get ahead of ourselves. Let's check this structure too and see if it would have the same thing. Odds are no, but let's check and see. Alright, so I kind of moved the bromine so we could see that 1 hydrogen that's there. Alright, so there's a CH3 here, there's 2 hydrogens there, and there's a CH3 there. So based off this, these 3 hydrogens only have 1 neighbor. So they would get 1 plus 1 or 2. I didn't see a doublet anywhere. Quite frankly, I could stop right here. But I'm not going to because I want to go ahead and practice all of them for you. Alright, so this hydrogen, right, lives in this house, right, has 3 neighbors over here and 2 over there. So it's got a 5 plus 1 or a 6. Okay. These two hydrogens have a neighbor here, 1 on this side, 3 on that side. So that would be a 4 plus 1 or a quintet. So both of these have a quintet and a sextet. And then these three have 2 neighbors. So that'd be 2 plus 1 or a triplet. So the big difference here is one of these had 2 triplets and one of them had a triplet and a doublet. So the fact that I've got the 2 triplets here makes me think that this is my product. Or, sorry, not my product, but this is the compound for my spectra. Alright, so hopefully that helps you on your journey. I will, I guess, post another video later. Bye.